So we have this heart problem where, so this side represents the left ventricle. So blood is going in here, and we have catheter over here. The outlet, we have the aorta, and which is represented as just regular T of temperature, and then just volume flow rate as just regular V. And catheter is represented with like V1 and T1, and then left ventricle V0, T0, or V0, T0. And we have to use a conservation principle to derive an equation for the total blood flow emerging from the ventricle and the transient temperature of blood leaving the ventricle. So actually, it's T, so which small t representing time, so it's a transient temperature. So let's use mass conservation principle first. So since the mass is not going to change, so dm over dt, which is represented as mass flow in minus mass flow out, and this is going to be 0 because mass does not change. And using that, we can say that the sum of m in is equal to sum of mass flow out. And so since we have two in from catheter and left ventricle, this can be represented as a m dot, so this is left ventricle, plus m dot 1 equal to just regular m dot. So that's one thing we can derive from the mass conservation principle. Now let's use energy conservation principle. Energy conservation. So dE over dt, which is a change in temperature, change in energy, can be represented as the Q dot minus. So this will be the case for if you're talking about the closed system where there's no mass transfer is occurring. But however, for our question, when there's a mass transfer, since the blood is going in and through the system, so there's a mass transfer happening, we have to take account for that as well. And in addition to this, we're going to put sum of m, so mass flow in times h in minus m dot out dot multiplied by h out, where h representing enthalpy. Because there's no work done, nor there's a heat transfer, so we can put dE over dt and m in h in minus m dot out h out. And we already know that m in, so we have two inlet, so m dot 0 h 0, and then plus, so that's left ventricle, and then m1 h1, which is for the catheter, and minus m out, which is our regular out, so m out, and just regular m dot times h. And we can also change it on the left side as well, from d over dt. So since energy is equal to m cp h, or not h, t, m cp t, but we're talking about the change of energy. So instead of, it's going to be dt, and then since we have small dt, we should have this as well. And we can see that the union works out. So, and you'll be able to see that once I change the h into a, you'll be able to see that the union works out when I change to m So H into CPT. So this is a specific heat, temperature, and then plus m dot CPT1 minus m dot CPT, and we'll have the same thing from the top on over here. Okay. So here, where we have the same CP over here, and instead of mass flow rate, we have just regular m here. And since the mass flow rate is just the mass divided by the time, well, that's why we have over dt is the change in time. So the units are same, and we have dt, and the unit of dt is just a temperature minus temperature. It's a difference in temperature. So actually these two have the same unit. So unit-wise, they works out. And the reason why they have just regular T instead of dt is because we're only interested in like the single inlet and outlet. So this is only representing a left ventricle. And left ventricle itself doesn't have any temperature difference. They all have same temperature. So that's why we have just regular T. And same thing as well over here. Oh, I'll forget the one. And this one is representing catheter. So catheter itself has the same temperature across it. So that's why we have T1 instead of just like dt, same as over here with the outlet. Now, what we're going to do is we can actually cancel, divide it by CP on left and right. And then we're going to divide it by m. So on the right side, on the left side, we'll have dt over dt. But since on the right side, we'll have m dot o over t0, t1 minus m dot mt is what we're going to have left with. And then we're going to isolate, we're trying to figure out what T is, the big T at the outlet or at the aorta. So we're going to isolate the T out. So if we move this T to the left, T term to the left, we'll have dt over dt plus m dot over mt. There we go. And same thing over here. Once you have this, so I'm gonna set t as y. So on the side, let's say t is gonna be my y. So this is going to be equivalent to dy over dt because t is my y now. And this m dot over m, I'm going to call it a. So we'll have ay because t is y. Let's write on the right side that my m dot over m is going to be my ya from now on. And this whole thing on the right, we're going to call it b. This whole thing is going to be b from now on. We can also write that okay. And so I'm going to isolate the dy over dt by moving ay to the right. So we'll have negative ay plus b, which can be rewritten as negative ay minus b. Okay. And I'm going to call this ay minus b as a big y. So we use small y. So in order to differentiate, I'm gonna call this ay minus b as big Y, like that. So because that is the case, the ay minus b equal big Y. So if we take derivative of both sides, we'll have dy over dt. Where on this side, if we take derivative, it's going to be a, just regular a, and then just dy over dt. And if we if we move this a to the right side, we'll have regular dy over dt is equal to big dy over dt, well, 1 over a big dy over dt is what we're going to get. So coming back to what we have over here, so we're going to solve this again. So this is this whole thing. If we continue with this, we'll have dy over dt was equal to 1 over a d big Y dt. So I'm gonna switch that to, on the left side we'll have 1 over a big dy over dt plus actually I made a mistake. So this is the whole thing, and I'm solving for this. So dy over dt, small dy over dt is 1 over a big dy over dt, because that's what we did over here. And on the right side we have negative ay minus b. But we said that ay minus b is equal to big Y. So we'll have negative big Y. And we're going to solve for Y, or the big Y. So now we can move all the Y, big Y to the left side. So let's do that. So Y over 1. And then dy is going to stay here, and then if you move the a to the right, it's going to be just regular a, and dt moves to the left, right, so a over a times dt. And we can solve for it. So 1 over big Y is equal to, if you take integral, so if you take integral of this, we'll have ln y, and on the right side we'll have at plus c, where c is the unknown constant. Then we can put the e so that the y goes away, but it is now e to the power of at plus c. Well, because of the rule, we can isolate this c out, so e to the power of c times e to the power of at, and this itself is just going to be another c, because unknown constant. Ooh, I made a huge mistake here, so I forgot to put the negative sign, so we'll have negative over here, so it's negative at plus c, and then we have negative, and then negative. Okay. So this is what we are left with, that big Y is equal to c e to the power of negative at. And we can later solve for c as well, knowing that our initial condition at time is equal to 0. So at time is equal to 0, temperature T, which is the outlet temperature, is going to be equal to the temperature at left ventricle, which is T0. And so this A is actually representative of m dot over m, and our big Y is representing AY minus B, where A is also the same thing, B representing this mass over here. So if you plug that in, you might get something like this, and you can solve for C.